When we're interested in finding the relationship between two variables, our most common statistical tool is correlation. So metaphorically, what we're doing is basically just designing a model or a structure where you have a y-axis and an x-axis, and then your data points are a cloud of data that's sort of scattered among the graph here. And the idea is that for every value of the x variable, there's some value of the y variable, and you have some relationship between these two. Now, this is a fairly straightforward thing to visualize when you only have two dimensions, when we're really only concerned about two variables. In this example, my intent was to show two variables that don't have a very strong correlation. So you can see the cloud is kind of scattered around, and there aren't any particular groups that jump out at us. But let's say, I'm going to do this by adding more data points, that it turns out that we have a structure like this. So here you can see what I'm trying to visualize is an area over here where we seem to have something going on, and then an area over here. So these two groups we can call clusters. So these clusters are areas where, in this case, looking at two dimensions, two variables, there seems to be some connection. So the idea of cluster analysis then is basically this idea of trying to find a relationship among different variables. However, instead of relying solely on bivariate correlation, where we're looking at two variables, cluster analysis allows us to look at relationships among variables along more than two dimensions. We use a technique that I'm not going to go into in any detail, but just for the record, the idea is Euclidean distance, as in Euclidean geometry. And so basically what cluster analysis does is, using a computer algorithm, you create a multi-dimensional space, and here let's pretend that we have 3 dimensions, and the software will look at your data and compare all the variables that you drop into it from 2 to infinity, hypothetically, although typically you're really working with just a smaller number of variables. And within this multi-dimensional space, the software algorithm will go in and find the groups or clusters that seem to be most closely related using this measure of Euclidean distance. So again, metaphorically, if you want to think of it, Euclidean distance is just kind of a 3-dimensional equivalent of correlation, where correlation is looking at 2 dimensions. So the important thing to keep in mind with cluster analysis is that you're not really able to explain any causality. It's not about cause and effect. It's just about, given a set of dimensions, variables, descriptors that mathematically have some similarity to one another, you form these clusters, and then the clusters are the starting point for your analysis. So once we go through this mathematical process of identifying clusters, what exactly do we do? How do we interpret what we found? There are different ways of visualizing clusters, but the technique that I like to use is simply to create bar graphs. So what I've tried to visualize here is 0, this horizontal axis, represents 0 as in the mean, the middle part of a statistical distribution. This is because part of the process of using cluster analysis calls for changing the numeric values of these variables from whatever their original values are, a decimal in the case of GPA, for example, or maybe a 3-digit number in the case of SAT test scores, a 2-digit number in the case of ACT test scores, whatever the numerical value is, it's converted to z-scores. And as a reminder, a z-score is basically a way of taking a set of numbers and dropping them onto a normal distribution, a bell curve, such that whatever the mean is of that set of numbers, that becomes 0, the middle point of the distribution, and then numbers that are less than the mean have a negative value. Let's say -1 would be -1 standard deviation away from the mean, and then numbers that are greater than the mean would have a positive value. So let's say, in this case, +1 standard deviation. So what this graph then visualizes is the starting point, or the baseline, is at the mean, and then here I just happen to have visualized 2 standard deviations below and 2 standard deviations above the mean. So what the software would produce then, the algorithm rather would produce, would be clusters that look like this. And here I just have 3 clusters, each comprised of 3 variables, just for the sake of presentation. What the variables are doesn't really matter for this discussion, but let's say one is represented by the dark colored or solid colored bar, one is this blank bar, and one is this dotted bar. And so here you have 3 clusters that, let's say, came out of this analysis. One cluster, you see the 3 values, whatever they are, whatever those 3 variables are clustered together because the folks here all had values for these variables below the mean. And as it happens, this cluster has a lot of blankness, whatever that is. That's why that's the biggest bar. And then a little bit less dottedness, and then least of all, this solidness. But the point is that this group clusters together mathematically, again, this Euclidean distance, because it happens that according to these 3 variables, mathematically, this is the relationship among these variables for this particular cluster of individuals. And then there are 2 other clusters that I've sketched out here. Both of these happen to be values above the mean, and yet even though these 2 clusters are above the mean, you see one has a higher value, is at or above 1 standard deviation, whereas the other one is well below 1 standard deviation, although still in positive territory. So again, the takeaway point is that when we look at clusters that come out of this kind of analysis, this is what you'll see. Now obviously these are just bars on a chart. So here, unlike correlation, for example, where we have a specific measure, R, the coefficient of correlation, we know that R, if we have a correlation between 2 variables that's perfect, for every unit increase in the X variable, there's a 1 unit increase in the Y variable. Here we know that R would equal 1 because the correlation is perfect. The 2 variables will move in unison. If we had no correlation, then we would have a value, an R, of 0. So the point is, when you look at simple correlation, this R value is kind of a ruler or a yardstick that gives us some idea, is this correlation strong or weak? Similar kinds of statistical analysis, like R squared for linear regression, have similar coefficients, similar yardsticks that we can use. Cluster analysis, fortunately or unfortunately, depending on your perspective, is as much an art as a science. Now, there are some mathematical measures that give us some idea about the probability, if you want to think of it in a metaphorical, not literal sense, the statistical significance of these different clusters, but I'm not going to go into those, both for brevity and because it would require a whole other lecture on Bayesian statistics. But suffice it to say, the purpose of this kind of analysis, again, is just to be a starting point. There are other analyses that can follow from it that might be more informative. But the takeaway is, in cases where you have a desire to try and find some relationship among multiple variables, and you have more than two, so instead of just simple correlation where you can look at the connection between two variables, you have this three-dimensional space, as I illustrated earlier, where you may have more than two variables that can describe some group of people. This cluster analysis is a good starting point. And I'll have specific examples at our next discussion.